Thank you, Nathan, for the sharing. It's great to see that different storage services can use the same key value engine. In Facebook, we also have different storage services for different scenarios. There are highly trafficked newsfeed or high throughput data analytics. When those different systems are managed and deployed in isolation, the resource utilization can be low. The next speaker today is Satadru Pan from Facebook storage team. He will talk about how we unify the storage backend with a new file system, Tectonic. Welcome, Satadru.
Hi everyone, this is Satadru. I am a software engineer in Facebook storage team. I work in Facebook Menlo Park office. However, because of pandemic, today I'll be recording this video from my home. Today we'll discuss how we consolidated our large-scale storage backends with Tectonic file system. Before going into the technical details, let's take a look at how Facebook uses storage. If you look at Facebook newsfeed, large portion of the experience is photos and videos. In fact, these photos, videos, and other media contents are collectively called blobs. Our blob storage infrastructure is responsible for storing and serving blobs shared across our family of apps. On the other hand, our data warehouse infrastructure is responsible for storing and serving Hive tables needed for our data analytics and AI training workload. Data analytics and AI training helps us provide great user experience by processing log events. Blob storage and data warehouse accounts for a large portion of our storage footprint, and we will use them as an example for the rest of the talk. As you can imagine, Facebook storage need to be highly scalable. In fact, both blob storage and data warehouse need to store multiple exabytes of data. To put things into perspective, we can put a 2-hour movie into one CD-ROM. To put 1 exabyte of data into CD-ROMs, we'll have to buy billions of such CD-ROMs. Another aspect of Facebook storage is its massive growth. As more and more users use our product and they interact more with our products, storage backends need to scale. In fact, as we will see in this talk, because of this drastic growth, often we need to rethink our storage architecture. Finally, these massive storage use cases often have very diverse technical requirements. In fact, blob storage and data warehouse are good examples of technical diversity. Where blobs are kilobytes to megabytes in size, the data warehouse objects or Hive tables can scale from gigabytes to terabytes. Their performance requirements are also very different. Blob workload is often latency sensitive because blob uploads and downloads are in the path of users interacting with Facebook. On the other hand, data warehouse applications often batch process data and they prioritize throughput over latency. Because of this technical diversity, we previously used different storage systems for these different workloads. To explain the previous point, let's take a look at how our storage infrastructure looked 6 years back in history, around 2015, within a data center. Our blob storage were split across Haystack and F4. Haystack used to store hot blobs with higher request rate, but it was not storage efficient. F4 used to store warm blobs with lower access rate, but it did not support blob uploads. Data warehouse used a set of HDFS clusters. HDFS is throughput efficient, hence suitable for data warehouse workload. However, a single instance of HDFS clusters can scale to tens of petabytes because of its single name node based design. Because of our growth, we had to provision multiple HDFS clusters within our data center to serve data warehouse workload. Moreover, HDFS was not suitable for low latency small appends. As a result, it cannot be used for blob storage. In short, none of the systems were generic enough to handle all the diverse use cases. Another problem with this setup was resources were poorly utilized and fragmented. For example, all these storage systems had different storage to I/O ratio. As a result, surplus IOPS from one cluster cannot be used by another cluster. Lastly, maintaining 3 different systems in production is operationally very complex. Engineers need to understand the details or functioning of 3 different systems and also their interdependencies. Also, common functionalities like disk repair, security, and like network protocols, etc., need to be duplicated. Now, fast forward 5 years in 2020. Tectonic is our unified distributed file system, which has replaced this previous constellation of storage systems made of Haystack, F4, and HDFS. A single Tectonic cluster can span an entire data center and provide storage for use cases like blob storage and data warehouse. This consolidation has simplified our operations because now we have to reason about only a single storage system which is capable enough to handle all the diverse use cases. Data center-wide Tectonic clusters also promoted better resource utilization because there is no stranding of resources in smaller clusters. As an analogy, you can think about it. Previously, we had a small set of buckets, so filling each of the buckets equally was very difficult. Now we have a large bucket, so we have completely removed this bin packing problem within the data center. This talk is about our evolution of our storage, how we moved from this constellation architecture in 2015 to this consolidated architecture in 2020. During this journey, we had to solve a couple of problems. First, the solution need to scale. Here by scalability, I mean each of the Tectonic clusters need to support the storage needs of an entire data center, which can often be exabytes. Second, the performance characteristics of this general system need to match the performance of previous specialized systems. As an example, for blob storage, Tectonic need to provide latency similar to Haystack. For warehouse, it need to provide throughput similar to HDFS. Third, the solution need to be multi-tenant. Tectonic need to isolate tenants from each other while enabling them to utilize spare resources. For example, a traffic spike in data warehouse should not affect the latencies of blob storage. Finally, stabilizing and rolling out a new storage stack transparent to the users of entire Facebook is a humongous task. It is like replacing engines of an aircraft while it is still flying. In this presentation, we will cover the challenges of scalability, performance, and rollout. Let's take a look how Tectonic architecture scales to exabytes. At the core of Tectonic, there is a set of independent storage nodes. Tectonic files are split into blocks. To provide durability, blocks are further split and read-Solomon encoded into data chunks. Chunks are stored as XFS files in the storage nodes in different failure domains. Tectonic chunk store can scale linearly with the number of storage nodes. On top of chunk store, there is metadata store. It is built using a linearizable, scalable key value store. In contrast to systems like HDFS, which store all the metadata into a single name node, Tectonic disaggregates the metadata into multiple hash-sharded layers. As an example, for the file system tree on the left, the name layer stores the directory to list of subdirectory and directory to list of file mapping. The file layer stores the file to list of block mapping, and block layer stores the block to list of chunk mapping. We can scale the metadata store by adding more machines that can host more shards. Finally, a set of background services talk to metadata and chunk store to maintain fault tolerance. Together, these components allow us to achieve exabyte scale cluster that can handle storage needs for an entire data center. Tectonic is a client library-driven microservice-based system. The client library orchestrates the file system logic by interacting with different metadata layers and the chunk store. We'll step through one read operation to see how client library compose the operations. To read from a file, in step 1, client library gets the file ID from file path from name layer. In step 2, it fetches the block list of the file from file layer. In step 3, it fetches the location of the chunks of those blocks. In step 4, it reads the data from the storage nodes holding those chunks, and finally return the data back. Similarly, on the right path, to add a block in a file, in step 1, client library gets the list of storage nodes from block layer. In step 2, it stores the chunks of those blocks into the storage nodes. In step 3, it saves the final chunk locations back in the block layer. In step 4, it adds the block to the block list in the file layer, and finally returns success to caller. As I mentioned before, scaling our storage proportionately to our rapid growth is challenging. This microservice-based architecture And lack of interdependence between these layers helps us scale each of the layers independently. As an example, we have recently re-architected our block layer without changing the file layer and the name layer. Now, along with this scalability, the client library driven orchestration also helps Tectonic meet the performance requirements. Let's take a look. To recap, the particular challenge for Tectonic or any general system like Tectonic is to match the performance of previous specialized systems. Specialized storage systems were optimized for their specific access pattern. For example, HDFS optimizes for throughput, but it was not good at low latency small appends. Tectonic uses tenant-specific optimizations to solve this problem. Tectonic client library, which runs inside the application, can be tuned based on the application-specific usage pattern. That's a good example of how Tectonic applies tenant-specific optimization. Warehouse files are typically big. They can scale gigabytes to terabytes in size. Another property of warehouse is that reads to these files happen only after the creator closes the file. Tectonic uses this pattern to minimize the byte written to upload a file to improve the overall throughput. Warehouse appends are buffered in client library till we get a full block. The client library then RS encodes the block in memory and writes the chunks to storage nodes. On file close, we attain read after write consistency by flushing any pending buffer data. Compared to data warehouse, blob storage has an entirely different access pattern. Blobs are small in size. As a result, blobs need to be appended to a log structured file on upload. Blobs also need to be persisted before acknowledging the upload. In other words, we need immediate read after write consistency. To solve this problem, Tectonic converts the small blob uploads into partial block appends. The triple replicated partial block appends provide immediate read after write consistency while minimizing the blob upload latency. To save space, once the partial block is full, the client library reads the data from the replicated block and then RS encodes it and stores it back. Directly storing RS encoded blocks for data warehouse reduces the IOPS and the total network needed to store a data warehouse file. On the other hand, to achieve low latency, blob storage spends more IOPS by writing the blobs first triple replicated, then reading it and then writing it back in a RS encoded fashion. This type of tenant-specific optimization helps Tectonic match the performance of previous specialized systems without losing its generality. Now that we have seen how Tectonic solves the problem of scalability and performance, let's see how we rolled out this solution to production. Usually rolling out any storage solution is hard, but at our scale, it becomes extremely complex. For example, all the photos and videos before inception of Tectonic need to be moved from the older system to the newer system. After we have started moving the data to this new system, we cannot very easily fall back to the older system because the data movement itself takes time. Basically, we need to validate that the new system doesn't have any performance regression, but also we need to make sure that it doesn't have any silent data corruption or it doesn't have any low probability edge case bugs, which takes a long time to find out. As a result, we had to run this new system in production for a very long time. To solve these challenges, we split the rollout into phases. In the initial phase of the rollout, we introduced Tectonic blob storage and Tectonic data warehouse clusters side by side with the previous systems. Initially, we had to over-replicate part of the data to Tectonic so that we can fall back to the older system seamlessly. We can validate the performance and add enough flight hours to the new system. For any large-scale migration, this in-transit phase is often very long and adds an additional operational complexity. We had to prepare by investing heavily in automated migration and verification tools. These tools are often as important as the new system. Once we are confident about the side-by-side performance, we slowly phased out the older systems. This phase-out step is done slowly, cluster by cluster, over next 2 years. So after almost 4 years of inception of Tectonic, we completely deprecated the older systems. But we are still not done. After this step, we consolidated the software, but the physical blob storage and the warehouse clusters were still disjoint and cannot share resources. Once we are confident about the software consolidation, we started rolling out the shared clusters to accomplish the cluster consolidation. This involved building appropriate multi-tenancy semantics, solving new scalability challenges, adding more verifications. Similar to software consolidation, this rollout was also done cluster by cluster very slowly. Splitting the storage consolidation journey into two phases, like first phase, the software consolidation, and then followed by the software consolidation, we do the cluster consolidation, helped us focus one hard problem at a time. In the first phase, we only verified that Tectonic is not regressing compared to our previous generation storage system. In the second phase, we verified the blob storage and data warehouse can coexist in a shared cluster and they do not have any adverse effect on each other. Now we have shared this 5-year journey. Let's take a look at some of the exciting results. On the scalability front, a single Tectonic cluster can scale to hold exabytes of data. That means a single cluster can store equivalent of data to billions of CD-ROMs, or it can also hold billions of 2-hour movies. This massive scale not only simplified operations because we now need to manage less number of clusters, but it also enabled better resource utilization because we can co-locate large use cases like blob storage and data warehouse within a single cluster. This chart explains efficiency wins from storage consolidation in a cluster shared between data warehouse and blob storage. The x-axis is time and the y-axis is IOs per second, or IOPS. In this cluster, both these tenants have almost equal space usage, so we can compare their relative IO temperature. In other words, the red line here shows the max IOPS corresponding to the space usage of those individual use cases. In other words, if the data warehouse and the blob storage bytes were stored in two different equal sized clusters, the red line would have indicated the max IOPS in that disjoint cluster. Now the green line shows the IO load from blob storage. As you can see, there is enough surplus IOPS. If we put this blob storage workload or blob storage bytes into a separate disjoint cluster, that cluster would have enough surplus IOPS. Now this saffron line indicates the data warehouse workload. As you can see, temperature wise it is much more hot, and more importantly, there are a couple of peaks where the workload crosses the max IOPS line. What that means is that if we put this data warehouse workload into a separate cluster, in that cluster we would not have enough IOPS to support these peaks. We'll have to throttle the traffic in those peaks. Because we are in a shared cluster, in those peaks, data warehouse can borrow the IOPS which was surplus from the blob storage workload. In short, multi-tenant clusters unlock resource efficiency by using the resources which would otherwise been stranded in disjoint systems. In conclusion, Tectonic is our data center scale storage system. By moving from our constellation-based storage architecture to this consolidated architecture has given us a couple of benefits. For example, we have got simpler operations because we need to manage only a single system. We also got resource efficiency because there is no resources stranded in these smaller clusters or between different small systems. In this talk, we briefly covered the couple of high-level challenges we faced to move to this consolidated architecture. For example, we saw how we scaled the Tectonic clusters to exabytes. We also saw how Tectonic matched the performance of previous specialized system performances. To learn about other challenges, our design, and a couple of other lessons of building and deploying Tectonic, you can look at our blog post, or you can also look at our paper which we published this year. And finally, thank you all for listening to this presentation.